Welcome. Dear students, today we are going to discuss about orientation and reactivity of E1 and E2 reaction. In part 1 of this video, we have seen the reaction and mechanism of E1 and E2 reaction. In this part 2, we will see reactivity and orientation of E1 and E2 reaction. So first let us discuss about reactivity. By reactivity, what we mean is that which of the alkyl halides would show higher probability to go for E2 reaction, okay, and E1 reaction. So first we will discuss about E2 reaction. For E2 reaction, which primary alkyl halide would choose the E2 reaction pathway? For this, let us take primary alkyl halide. Now, let me remind you, in E2 reaction, there is no carbocation. A carbocation is not formed. Carbocation is not formed in E2 reaction. Primary alkyl halide, its carbocation is primary carbocation. And you know that primary carbocation is very unstable. It is very unstable. So ionization of primary alkyl halide to primary carbocation is not favored because the primary carbocation is very unstable. So its ionization is not favored. And as you know that E2 reaction does not have carbocation in it, therefore a primary alkyl halide would always choose the E2 pathway. It would always choose the E2 pathway. Primary alkyl halide would never go for E1 mechanism because in E1 mechanism a carbocation is formed and that carbocation is very unstable. So it would never go for E1 mechanism. Primary alkyl halide would always choose the E2 mechanism because it does not involve a carbocation. Let us see the case of tertiary alkyl halide. Now, a tertiary alkyl halide, let me draw one tertiary alkyl halide, tertiary butyl chloride before you. Now, this is the base. It wants to take a proton. It goes for elimination rather than for substitution. So it wants to go for a proton. Now, how many carbon atoms are there? This is alpha carbon atom 1, alpha carbon atom 2, beta carbon atom 1, beta carbon atom 2, beta carbon atom 3. This is alpha carbon atom. There are 3 beta carbon atoms. So there are 9 beta hydrogen atoms. So the probability of getting a hydrogen in tertiary alkyl halide is more rather than primary alkyl halide. The probability of knocking out of a beta hydrogen atom is more in tertiary alkyl halide rather than a primary alkyl halide. So if such is the case, then it will also undergo which kind of reaction? E2 kind of pathway. It will choose E2 pathway because it has more number of beta hydrogen atoms. So more chances are there. But tertiary alkyl halide would choose E2 pathway only under certain conditions, under certain situations of the reaction. The two conditions are, there are two conditions. Condition number 1 is leaving group. It should be weak. Okay, leaving group should be weak. Weak leaving group. Why weak leaving group? Because if it is strong leaving group, a carbocation will be formed and it will go for E1 reaction. So therefore the leaving group should not go. It should not go very fast. It should go only after the base has attacked, right? So it should be weak. And second condition is base should be strong. Strong base. So that before the leaving group grows, the base abstracts a proton from the beta carbon atom. If these two conditions are satisfied, then tertiary alkyl halide would also go for E2 mechanism. So In case of secondary alkyl halide, the story is like the same only. It would go for E2 mechanism if there is a weak leaving group and if there is a strong base. Secondary alkyl halide would also go for E2 reaction if these two conditions are satisfied. Now, dear students, you might have noticed that in SN1, SN2 reaction, we have given an ascending order of reactivity, which is more reactive, we have given an ascending order of reactivity. In this we cannot give any ascending order or descending order. It entirely depends upon the reaction conditions, the base that is used, the leaving group that is used, and we have seen that in the case of tertiary alkyl halide how it will go for E2 mechanism, in what conditions. Condition number 1, if the leaving group is weak, and condition number 2, if the base is strong enough. So in these two conditions the tertiary alkyl halide would go for your E2 reaction. Now let us see for E1 reaction. Let us talk about E1 reaction. E1 reaction, your primary alkyl halide would never go for E1 reaction, because it would never go for E1 reaction, because a E1 reaction involves carbocation, and the carbocation of primary alkyl halide, that is a primary carbocation, is very unstable. Therefore its ionization to primary carbocation is very unlikely. Therefore it would never go for E1 reaction. A primary alkyl halide would only go for E2 reaction. Then which goes for E1 reaction? Tertiary alkyl halides would go for E1 reaction. Tertiary alkyl halides. Let me draw tertiary alkyl halide. I am going to draw tertiary butyl bromide. This is the tertiary butyl bromide, or chlorine tertiary butyl bromide. Okay. There is, look at the nature of this. It's very highly polar. All groups are pumping. Carbon itself is pumping its electron, and bromine is electronegative. It withdraws. So a very high polarity exists. Dipole exists in the molecule. This side being positive, negative. This side being positive. So it is bound to dissociate, and therefore it is bound to form a carbocation, and therefore it is bound to go for E1 reaction. It is bound to go for E1 reaction. But there are two conditions. Condition number 1, the leaving group X should be strong leaving group, so that it ionizes fast, strong leaving group. And second condition is that base should be weak. If these two conditions are prevalent in the reaction, then tertiary alkyl halide would go for E1 reaction. If opposite is the case, if the leaving group is weak such that it does not ionizes, and the base is strong such that it knocks out a proton, then it would always go for E2 reaction. But if this is the case, when the leaving group is very strong enough, it would immediately ionize and it will go for the E1 reaction. For secondary alkyl halide, the situation is the same. If the strong leaving group is there, if the base is weak, then secondary alkyl halide would also opt for the E1 reaction. But however, one thing is very sure, a primary alkyl halide would never go for E1 reaction, because a primary carbocation is very unstable. Like in SN1 and SN2 reaction, we cannot give an ascending order or descending order of reactivity, because the reaction depends upon how is the base and how is the nucleophile, how strong or weak is the base and how strong or weak is the leaving group. So the reaction depends on reaction conditions. Now let us discuss about orientation. By orientation, what we mean is that if there are two or more than two beta carbon atoms, then from which of the beta carbon atom a hydrogen will be eliminated. That is what we mean to say by the term orientation. Let us discuss orientation with an example. So I am going to take 2-bromobutane as example. This is 2-bromobutane. This is the alkyl halide. Okay. Now I introduce a base into the system, OH minus. Okay. And elimination reaction is going to take place. So OH minus can either knock this proton, that is case number 1, or OH minus can knock out this proton, which is case number 2. So if case number 1, in case number 1, what do we get? H2C CH double bond CH2 CH3 CH2 CH2, that will be 1 butene. If second is the case, then what would we get? CH3 CH double bond CH CH3, that is 2 butene. So as we can see in this example, 2-bromobutane have 2 beta hydrogen atoms. One is here and the other beta hydrogen atom is here. So there are 2 options. OH minus can either knock out from this beta carbon atom or it can knock out from this beta carbon atom. So 2 conditions, according to the 2 options, 2 products will be formed. One will be the 1 butene, the other one is 2 butene. So by orientation we mean which of the beta hydrogen atoms will be knocked out. That is what we mean by orientation. So this question is solved by the Saytzeff rule. Saytzeff rule states that in case of dehydrohalogenation of alkyl halide, if there are 2 alkenes formed, the major product will be that alkene which is more branched. Accordingly, 2-butene will be major product. Let me repeat the Saytzeff rule. According to Saytzeff rule, what Saytzeff rule says is that if there are in dehydrohalogenation of alkyl halide, if there are 2 alkenes that are formed, 2 or more alkenes that are formed, then in that case the major product, the major alkene will be that one which is more branched. Now why this one? Why not that one? This one, because the alkene, it is in the double bond is in the center. The pi electron or the pi cloud is shielded by steric groups on both the sides, right? It is shielded by steric groups on both the sides. You can see here there is a CH3 here. Okay, there is a CH3 here. Okay, this is cis isomer. Consider it as cis isomer. So there are steric groups on both the sides that can shield or protect the pi cloud. So it would be very difficult for electrophile to attack the double bond. It is much difficult in this case. In this case, in 1-butene, what is the situation? There is only, this is H, in 1-butene, H. This is the situation here. So there is a, so there is 3, 4. So there is a steric hindrance only from one side. So electrophile can easily attack 1-butene's pi cloud, right? So it is much unstable. It is unstable compared to this one, 2-butene, where steric groups are on both sides and both steric groups, they shield the pi cloud very effectively. So this is a much stable alkene than this. So this will be formed as the major product. This is what Saytzeff rule says about the orientation of orientation of E1 and E2 reaction. Dear students, I hope you have understood the class. If you like the video, please do not forget to subscribe the channel. Thank you very much.